Yeah.
Welcome, everyone. It's my pleasure to introduce Thomas, who's going to be talking about quantum groups and vertex algebras.
Yeah, thank you, Flora. So Simon is also here, and Simon, my former student Matt Rupert, and I, a few years ago, we wondered whether we can kind of understand this relation between vertex algebras and quantum group conceptually, and it seems we now got it more or less. So and this is what my talk will be about. And let me start by first telling you why I think this is important. Of course, it's always important and interesting if you relate different areas of mathematics or so. But both vertex algebras and quantum groups, they became interesting and important because of physics. We all know this very well, right? And if you think about physics, a physicist doesn't necessarily want to think about two-dimensional conformal field theory. He really wants to think about an honest quantum field theory in four-dimensional space-time. And we all know that this is a highly difficult problem, right? So that means, and we know that these four-dimensional quantum field theories, they have a high impact on modern mathematics in general. So and of course, a rigorous formulation of four-dimensional quantum field theory is totally open, and you would be more than famous if you would make a good statement in that direction. Now, what does a physicist, and maybe not only a physicist, but also a mathematician usually do is he tries to find good invariants of the supposedly physics that he can describe. And so usually you think about this as this four-dimensional theory has some kind of symmetry, for example, some kind of supersymmetry. That always helps, because then you can pass to protected sectors, so some kind of VRST cohomology, and that might have then a chance to have a much better description than the whole theory. And so the way one thinks about it, so you have certain operations that you should think about as some kind of cohomologies associated to the quantum field theory, some kind of protected sectors that are better behaved, and you can think about them as lower dimensional theories. And there are two classes of lower dimensional theories that one kind of likes in particular, and these are three-dimensional topological field theories and two-dimensional conformal field theories. So TFT for topological and CFT for conformal field theory. And now if you look at this historically, we know this has a huge impact. In fact, probably without this picture, we wouldn't know much about vertex algebras or quantum groups. Well, quantum groups maybe we would, but we know that vertex algebras definitely come from physics. And in this direction, there were two key results. One, of course, due to Edward Witten, and I mean, what did he get his Fields Medal for? He realized that invariants of knots and links are computed by certain correlation functions of certain operators called Wilson loop operators in a three-dimensional topological field theory. Let me write this down. And this is kind of the simplest type of a topological field theory. And this topological field theory is called Chern-Simons theory. It's attached to a positive integer, a level k, and a compact Lie group. And then more or less simultaneously, on the mathematical side, maybe more, Von Jones with his subfactors, he realized that invariants of knots can also be computed. And while his motivation, I mean, while he's coming from the subfactor region, it's best formulated in terms of coloring the knots and links in terms of representations of a quantum group. So Jones also realized that you can compute invariance of knots and links, and he got the same result as Witten if you take the correct gauge group. So, and what did he realize? That they are computed as the invariance of ribbon graphs colored with modules of quantum SL2. And I should also mention now Reshetikhin and Tuarev, because they are the one that then made this very precise in terms of braided tensor, modular tensor categories, and so on. Now, so this means if you want to have a picture, you choose your favorite color. So here my favorite color is red, maybe standing for some module of quantum SL2, for example, the standard representation, and then you take the trefoil, and you can you draw the corresponding ribbon graph, and this coloring means the crossing, you associate a braiding to it, etc. And this means this colored ribbon graph, you associate a number to this, coming completely being determined from the representation category of quantum SL2. Okay, I hope I'm not boring you, but I kind of like to start with a little bit of history. And now, in particular, because this history, even though it's 30 years ago, 30 a little bit, it's kind of very modern, because while this for a long time, this has been more or less the state of the art. Of course, there has been progress, but not totally substantial, maybe. At the moment, I would say there's a really big progress, because so in particular, there's this group around Constantino, Nathan Gear, and Bernard Patio-Miron, who developed a framework of invariance of knots and links, and in fact also complete three-dimensional topological field theories associated to non-semi-simple categories, and maybe also not finite categories. So it's very interesting. And of course, you also want to understand not only the mathematics behind it, but you also want to have a good physics picture behind. And I have this short note with Tudor Dimofta et al. So also Nathan Gear is part of it. So we kind of were a good team, because we had Nathan, who knows all these TFT story. Tudor, he's fantastic with all the physics. Nick Garner is his former PhD student, and then I was part of it. So what we try to define a three-dimensional physical topological field theory that exactly realizes this TFTs that also mathematically arise. And this is kind of informative, because physics is always of the type that it can be phrased in many languages. Right? A physicist is not just doing a vertex algebra, or not just doing quantum groups. He somehow has input from many directions. And so I mean, these topological field theories, we know they are attached to representation categories of something nice. And physically, these are the line operators. So some kind of lines inside 3 dimensions. It's a 3-dimensional theory, and but it's very hard to attach a category to a line operator. Anyway, so this is what what physics is interested in. So how can you relate this to something maybe more precise? Well, there was for that you have to ask Kevin Costello and Davide Gaiotto. So they realized that these categories admit what's called holomorphic twists, or better say these theories, these topological field theories. I mean, they admit the three-dimensional theories. They admit holomorphic twists, and these have the property that the endpoints of the line operators can be associated with boundary VOAs. So boundary just means that the VOA live on a two-dimensional boundary of the three-dimensional space-time. So this is Costello and Gaiotto. And now, of course, you're looking for a brighter tensor category, and the VOA should have that. So the proposal is, of course, that the category of line operators is precisely the category of this boundary VOA. And then this is where now VOAs become very much into the game now. But you can, of course, also ask other question. Do you have an associated quantum group to this category? And this question is maybe a little bit unmotivated. So let's ask another question. Do you have, so what does the physics do? The physics is formulated in terms of some kind of action, some kind of Lagrangian. And in particular, these line operators are described in terms of these. And one thing one can extract from that is, in fact, one can extract some superpotential in the language of matrix factorization. So matrix factorization is a geometric way to get, again, also good tensor categories. So you can, and they also come kind of quite natural from the physics. So a maybe much better question would be, is there an associated category of matrix factorizations, for example? Now, I don't know much about it, but I'm discussing a lot with Tudor and his PhD student Benjamin New, and it turns out that at least in baby examples, it's possible to relate the matrix factorizations to quantum groups. That's the motivation for putting the quantum group here. And so in particular, you should think about this as a triangle, square, or maybe a bit larger. Anyway, you have a bunch of options to realize braided tensor categories, one of them being a VOA, maybe what we are here in this talk mostly interested in. But there are other types of categories that are also somehow naturally motivated from to physics, and the quantum group is maybe the one that is least motivated. Maybe I'm also false with that statement, but I think the quantum group is the one that that is so much hands-on, right? A quantum group is something very concrete. So this means I think you want the quantum group in the game because it's maybe the thing that you can relate everything well to. And so this is a very long introduction. I just wanted to say a few words that I'm not only interested in the quantum. So I'm interested in the quantum group VOA correspondence for its own benefit, just because it's quite nice and neat. But there's more to it. It should be viewed as interesting from a much bigger perspective. Okay, so this is part one of the talk. Now, I want to tell you how could we possibly prove that a given VOA category is the same thing as a quantum group category. Well, categories are complicated, and so the idea should be somehow we need to have some kind of reconstruction scheme. We want our categories to appear to be realized from somehow simpler categories, and I will now try to make this precise. So maybe the guideline we have in mind is there are few VOA categories that we can very easily describe. So the simplest example is the category of modules of a lattice VOA or the category of modules of a Heisenberg VOA, because that category is just graded vector spaces graded by the corresponding abelian group with a certain twist, a certain O cycle, and that's it. So maybe we can kind of relate to such a structure, and that is in fact what we want to do. Okay. So in this talk, I will the starting category will be U, and you think about as the category of modules of our quantum group or of our VOA. And now we want to have a theorem that says U is equivalent to something that is coming from kind of more basic structure. And what we use is the thing that I think has already appeared quite often in all these talks is we use the framework of commutative algebras and tensor categories and so on. So let me repeat this quickly. So we start here with a triple AM iota, which is an which we call an algebra in our category. So here the A is an object, and M stands for multiplication. So morphism from A times A to A, and iota is an embedding of the tensor unit in the algebra. Now, what do you want for an algebra? Well, maybe you don't care about whether the algebra is commutative or not, but definitely you want to have an associative multiplication. Right? So we see here we can first multiply the two right components and then multiply again, and we get A. And on the right hand side, we can first multiply the two A's on the left and then multiply again. And we say this is an associative algebra if this is a commutative diagram. Now, in addition, one often wants the algebra to be commutative. If, in addition, the multiplication is commutative, so here by C, I now denote the braiding, the commutativity constraint in the category. And what can we do is we can first multiply, or first braid and then multiply. And that's, of course, the obvious notion of a commutative algebra. Okay. Now, why do we do this? Because if we have a commutative algebra, we have two categories attached to it. And these two categories are the simplex structures that we kind of need. They are, of course, not always simpler, but in our setting, they are. So we define another category that we call B for Borel. So this B, we want at the end to associate with Borel. So this is called the category of A modules in A. And so this in our base category, and here it consists, for example, objects are pairs, X an object in our original category. And what do we need if we want this to be A modules? We surely need an action of our algebra on the object. Now, this is a tensor category, but not necessarily braided, but it has a subcategory that we call C for Cartan subcategory, Borel category, Cartan subcategory somehow. You'll see in a bit why we call them like this. And this is a subcategory of our Borel category, and it's the category of local modules. And what does locality mean? Locality means you kind of so let's see. We want to have a commutative diagram. So what kind of operation, non-trivial operation, do we have to go from A times X to A times X? Well, we can once braid from A times X to X times A, and then braid back. And we very well know in a braided tensor category, as long as it's not symmetric, this is typically not the identity map. So the locality constraint is kind of a severe constraint. It corresponds essentially to locality in the VOA setting. I mean, yeah. So, and the point is that this category is a braided tensor category. Okay. I think most of you know this, so I hope that was not too boring. Now, what do we want to do is, so the point is, we want we want to relate our U to B, in fact to a mix of B and C. So you will see, but B is just a tensor category. It's not a braided tensor category. So it can't be just B as such, but to any tensor category, you can associate a braided tensor category by passing to its Dirichlet center. So so that means we take the center of a category, and now I just write down the center of U to have it for, and I mean U is now any tensor category again. So, and what is the center? The center has objects, Z and gamma. Objects are pairs, Z, gamma, where Z is just an object in our base, our underlying category. And gamma is something that is called a half braiding. So that means gamma is a natural family for every object in U, a morphism from X times Z to Z times X. And this is so, and this is a natural family, and it's coherent in the sense that it satisfies the hexagon axiom. So exactly the hexagon that you have for braiding. When for braiding you have one for the braiding, and that's inverse. And here it's a half braiding. You only have one hexagon. So what you do is you write down X times Y times Z and Z times X times Y. And then you think about how can you pass from the left to the right, just using associator and half braiding. And so what can you do is you can first associate and then do the half braiding for the object X times Y. And then you can associate again, or you can first do the half braiding for the object Y, associate, and then do the half braiding for the first object X. So the kind of obvious coherence or axiom. Now the point is that the center is always braided, and the braiding of morphism is the thing that you can obviously write down. So you take two such objects. What could possibly be the morphism from where you change the order? Well, this is exactly what gamma tilde Z does. All right, so and it turns out this exactly gives you a braiding. Okay, and typically this is not a symmetric category, right? Because the double braiding is the composition of gamma tilde with gamma. So there's no reason for that to be just the identity. Okay, now now let's assume we have a subcategory of the center. Then one can define the relative center as the centralizer of the subcategory in our center. And what does centralizer mean? This means these are objects that they have the property that the double braiding but the double braiding is just the identity for any object in the subcategory. Okay, and now the idea is we take for our U actually the Borel B. So bad preparation from my part. I should have written this like this, and we would like to claim that for our original category U, the relative center of B relative with respect to C to this category of local modules is very closely related to our original category. And this is our first technical result. So of Simon, Matt, and myself. And I should also say that it uses a really good result by Peter Schauenburg. So, and it says the following: if our categories satisfies a few good basic properties, so our starting category, we unfortunately needed to be rigid, but interestingly, we need rigidity only in a tiny step. So we kind of hope that one can eventually get rid of it. So we needed to have a few properties. So locally finite is very much essentially, of course, we wanted to be braided category, rigid, and trivial Müger center, so no transparent objects. And then we need an A to be a commutative and haploid algebra in U. And then we need the category of A modules to be rigid as well. So these are the properties. So haploid is something that is in fact most often satisfied. It means that the tensor identity has multiplicity 1 in A. So it's something very natural. So under these conditions, we have that there is a fully faithful functor from U to the relative center of B relative to C. So I say it in words again. B is the Borel, the category of A modules in U, and C is the category of local modules. Like maybe it's good if I recall this. So this would be the lengthy way to write it. And now, of course, we fully faithful means it's injective. And now we also want it to be surjective. And that is, in general, a very hard problem. Surjectivity seems to be the key problem in all these types of problems. So it's also surjective. That means it's an equivalence if one of the two is satisfied. So if U is a finite category, we are already fine. So this is thanks to a result by Shimizu. So Shimizu saves us because in finite categories, there's a notion of dimension for Venus-Perron dimensions, and then you can just compare dimensions. It's a one-line computation to get this surjectivity. It's very much for free. Now, in the non-finite case, thankfully, we have Simon. So he was watching here. Hi, Simon. So then we have that if all our categories are realized by finite dimensional representations of some algebra, each of some algebra, which for the quantum groups is automatic, because then it's you'll see that then in examples. So, and maybe as a remark, right? I already said that we don't like the rigidity assumption, just because in the VOA setting this is so hard to prove, and we very much hope that we can do it without it, but you maybe one simply needs more experience with categories. So the rigidity was needed in order to show that the proof passes through an embedding of U times U reversed into the Deligne product in the center of U, and you need to show that this embedding is fully faithful. And in order to get that this embedding is fully faithful, we needed rigidity. So, which in fact should be a textbook result in TensorCAD. It's just that unfortunately, beyond finite tensor caddies and centers, there's more or less nothing done. And so okay. Anyway, now let me conclude with a few examples. So all I wanted to say is in this talk, this theorem, and now I will explain to you why it's a good theorem. So no big surprise that I will start with a quantum group. So, for example, we can take the small quantum group. I could also put an H for an unrolled. It doesn't do a big difference. And Q, we of course wanted to be a root of unity, and usually we want it to be an even root of unity. Now, how can I find a C in a quantum group? These quantum groups have a triangular decomposition. In particular, they have a Cartan subalgebra. Cartan subalgebra is in particular commutative, something very simple, right? So this quantum group is graded by a Cartan subalgebra. And of course, H and our C that we want to have is here just the category of modules of this Cartan subalgebra, say weight modules. And that is, of course, just vector spaces graded by this abelian H. And what is the B? Our B is the representation category of the non-negative part of the quantum group. And so yeah, let me maybe be a little bit more explicit, just because we all know SL2 best. And SL2, the quantum group, is just generated by E, F, and K. So the element in the Cartan subalgebra is usually called K. And I don't write down the relation, but the Cartan subalgebra is then just the algebra generated by K and K inverse. Recall in the small quantum group, it satisfies the relation that its 2p power is equal to 1, and then the Borel would just be the polynomial algebra in E with coefficients in H, subject to the relation that e to the p is equal to 0. So also quite simple. Now, and here we can apply this statement, and it would just say that the full category of the quantum group is this relative center of the Borel relative with respect to the Cartan, and this relative center is identified with Jeter-Drinfeld modules. So it's also something one knows. Now, this is of course not the point of my talk. The point of my talk is the next example. So the next example is the singlet VOA. It's called usually MP, and P, we have one such VOA for any integer greater than 2, greater or equal to 2. And so these singlets are the cousins of the triplet, which is maybe more famous, but the singlet is maybe more fundamental because much more comes out of it. Luckily, Robert and Jinwei and I, we finally understood the complete category of the singlet. So we have complete control over it, which was difficult, definitely. So now we would like to have the same kind of same kind of statement for the singlet. So we have the singlet algebra, but now how can we possibly find a Cartan subalgebra, and in particular, it should be the Cartan subalgebra. I mean, the algebra whose representation category is equivalent to the Cartan subalgebra of quantum SL2. And now we can think about it. Well, quantum SL2 Cartan is abelian generated by a single element, right? So if I take unrolled, it would in fact be freely generated. There wouldn't be relations because of the unrolling procedure. So this means in the unrolled case, it would just be C graded vector spaces. But which VOA has representation category C graded vector spaces? This is a question you could ask a student at an exam on a VOA course, right? And the student would know the answer. He would say Heisenberg. And so next question would then be, well, good, but what does the Heisenberg VOA have to do with the singlet? As maybe not for this you have to know something, but the nice thing is, how is the singlet algebra realized? It is that is how people came up with it. They looked at the Heisenberg VOA and they thought, well, the Heisenberg VOA is too boring. Can I somehow find a more interesting VOA in it? Well, of course we can, right? We know that the Virasoro algebra lives in there and it's characterized as the kernel of a screening charge in there. But now if you take this, the level for the central charge for the Virasoro corresponding to this P here, then it turns out the kernel all of a sudden becomes much bigger, becomes the singlet algebra. So anyway, long story. The point is our Cartan subalgebra is H mod, named where here our curly H is the rank 1 Heisenberg algebra. And let's also recall, why does this make sense? Because we have here an embedding of the singlet algebra and the Heisenberg algebra, and this Q here, I didn't even look up what it is. It's a certain simple singlet algebra module. It's not relevant for us what it is. So in particular, the Heisenberg VOA is a commutative algebra in the category of singlet modules. It's a funny commutative algebra, but because it doesn't decompose into a direct sum of simples, the singlet modules, it's a single indecomposable module. But if you think about it, what's the Borel? I mean, no, this I didn't want to say that. Anyway, this is kind of a key property for us, though. Anyway, our Borel we now define to be the category of modules in U that are modules for this commutative algebra called the Heisenberg algebra. Okay. And now one does a computation, which in fact takes a bit of time. So, and unfortunately, I had to do it. So anyway, the point is now you simply work a bit in order to completely characterize this category UH. And after a few pages of carefully looking at it, you get, in fact, that this category is equivalent to the Borel part of the unrolled quantum group of SL2. G here is an SL2. Yeah, and this is in fact as tensor categories. So he and then, but now we have that U and I mean Cartan and Borel of a singlet and unrolled quantum group are the same. So relative centers are the same, are equivalent. So this means one gets for free from this discussion that in fact the conjecture that the category of weight modules of the unrolled quantum group is the same as the singlet category is in fact true. So it shows. I mean, this is what we wanted, right? And but but really what we wanted is we want to have a procedure that this is just a special case of something really nice. And so if I want to claim that, I probably have to say more, right? Because now I guess I have to convince you, or I don't have to, but I'm personally convinced that one can do an enormous amount of this. So, and I came actually to vertex algebras because of these super algebras. I've always been interested in them. The problem is just these super algebras are complicated, much more complicated than what we, I mean, they are, yeah, it's just not, and but they exactly fit into our framework here, or let's say half of them fit. If you classify basic classical Lie super algebras, they fall into type 1 and type 2, 50-50 roughly. And type 1 means that your Lie super algebra allows for triangular decomposition, where this G naught is the even subalgebra, and the B minus and G plus are odd. So so what do you want to do here? So clearly you have a positive G, I mean a non-negative one, namely G naught plus G plus. And now so one thing you can kind of immediately do is you can, on the level of quantum groups, you can look at the quantum group of G naught. So here our C, even though it's still called C, is not a Cartan and it's not abelian anymore, right? It's just the quantum group of some Lie algebra. And our Borel will be the Borel, I mean you should call it parabolic Borel of the supergroup. And you can reconstruct, and that would give you the statement that's clear that the quantum supergroup can be also characterized as a relative center of the category of B modules relative with respect to the even subgroup. And now the interesting thing is you can very naturally mimic this on the VOA level, and it gives you a straightforward path to probably eventually prove Kastanustik for supergroups. And that's maybe really the true motivation. I mean, or let's say the very big hope that yeah, this is my very big hope. And I think it's realistic that maybe in 5 years I'll sit here again and I'll say it does indeed work. I think it's not totally long. I mean, 5 years is surely realistic, maybe even less. And one reason is so now you of course also want to do something on the VOA level, and now in particular Robert, Jinwei, Shashank, and I, we kind of have made some substantial progress in understanding how to get tensor category structure, and also, and Flo, of course, you also, and also how to understand this tensor category structure. And in particular, Jinwei and I, we had a really nice criterion that gives us existence of tensor category, and this applies super well. So VTC stands for vertex tensor category, Braid's tensor category, to Lie super algebras, in fact. If one restricts to the Kastanustik category. So Kastanustik category means that that every conformal weight space is a finite dimensional G module on which maybe also with a semi-simple action of the Cartan subalgebra if you want. So it's the usual Kastanustik category. And as long as you take your level to be irrational, you get this. This is a non-trivial result, in fact. I mean, for Lie algebras, it's totally trivial. It's also not I mean, it's not it's not. All I want to say is not obvious. Now, so this is already good, and it's also okay to verify that the fusion rules are coming from the finite dimensional from the horizontal subalgebra. Now, now you also need to find kind of the good free field realization, and there's something that's called, I think it has never appeared in the literature, but it's well known. You have some kind of parabolic vacuum-motor free field realizations. Right, because for usual vacuum-motor free field realization, you take the usual triangular decomposition, negative roots, Cartan, positive roots. But you can also do a splitting, like here in the superalgebra case. Your Cartan is replaced by G0, some kind of diagonal block subalgebra, and then you still have a negative and a positive block. Now, whenever you have this, it's not really a hard problem to show that you have an embedding of the affine VOA in the even sub VOA in our case, times a free field algebra corresponding to the positive and negative block. So here the free field algebra are BC systems, they are fermionic, and you need as many as the dimension of your positive or negative block. They have the same size. And here this K tilde is easy to compute. I just downstate it. It just depends on the G0 action on G plus. So for example, if you take SLN/M, you have N times M BC system. They have a commuting action of SLN at level M, SLM at level N. And so then K tilde will be K minus N on the SLM, K minus M on the SLN. And yeah. Now the next task, and I'm very optimistic that this is a very doable task, is to show that this Kashtan-Lusztig category is abelian equivalent to the quantum group category of G, where Q should be e to the 2 pi I divided by 2. Are you still there? Just something appeared on my computer.
We are here.
I think Q should be this. Maybe, but in fact, the computation can show what it is. Okay, so let me summarize. So the idea is that the VOAs that we know, they always have good free field realizations, right? We know singlet and triplet, they live in a Heisenberg algebra or lattice VOA. There are the higher versions that Shoma Sugimoto worked on. The Fagin-Tipunen algebras, they have similar free field realizations. If you, in particular, Dražen Adamović has used the free field realizations of admissible level affine VOAs a lot. And their free field really means, for example, as affine SL2 embedded into Virasoro times some kind of half lattice VOA. So having these free field realizations is a current theme. So that and now for Simon, Matt, and me, this means now it means that our difficult category of modules of the VOA has a much simpler commutative algebra. Much simpler in the sense that its category of VOA modules, of local VOA modules, is something much nicer, right? It might just be the category of modules of a Heisenberg or lattice VOA, graded vector spaces. On more complicated cases, it is at least a category that is of simpler degree of difficulty. And the theorem that we have is, as long as we understand this simpler category well enough, but well enough is still means a lot, because we also need the not only the braided tensor category, but the complete category of modules in the bigger category to understand. But the point is, our statement is, if we understand this category well enough, then essentially we don't even need a conjecture to a quantum group. We can kind of reconstruct it. The knowledge of this rep, of what we call B, this UA, the knowledge of this one more or less tells us what is the corresponding quantum group, or more general, it will be, of course, not a quantum group, some quasi-Hopf algebra or something along these lines, and we will simply get it. So this is kind of nice. And so let me maybe finish here and just stop by showing you the main theorem again. So the theorem is, as long as a bunch of assumptions are satisfied, presumably the only complicated assumption here being rigidity, unfortunately, then we can reconstruct. And we also strongly believe that we can improve this theorem. But for the moment, we decided to stop here, write it up, because we've been working on this for many, many days, months, years, decades, centuries, all this. Anyway, thank you for your attention.
Thank you so much, Thomas. Are there any questions for Thomas? Please feel free to unmute yourself and ask. Let me stop the recording so maybe people will feel more comfortable asking questions.